Hello everyone. In the previous discussions, we have seen about Umpolang reactions and how an Umpolang system is useful for synthesizing a target molecule which could not be achieved with the natural synthons. In this particular discussion, we will be observing for one group CX disconnections. That means we would first try to disconnect one group which is attached to an heteroatom, and further we will be using this particular strategy in a retrosynthetic analysis so that we can achieve our final target molecule. So what is this one group CX disconnection? The CX disconnection approach to a carbon chain attached to any of the heteroatoms like oxygen, nitrogen or sulfur. Mostly one group CX disconnection are utilized when we observe there is a presence of oxygen, nitrogen or sulfur which are heteroatoms. Here a bond joins the heteroatom X. That means this X is said to be either oxygen, nitrogen or sulfur to the rest of the molecule. Now the rest of the molecule can be containing a carbon system forming C single bond O, C single bond N and C single bond S group respectively. Now why do we choose this particular bond? Because it is a good point to initiate a disconnection. So if we choose these particular bonds, we can say that easily we can disconnect the system and we can do a retrosynthetic analysis, and also we can arrive at a synthetic equivalents which are easily available, and further utilizing those synthetic equivalents we can achieve our target molecule. Now this is called one group CX disconnection, as one would need to identify only one functional group. What we need to identify in these molecules or these target molecule is only one functional group. Now that can be an ester functional group, ether functional group, amide functional group, where we can try to do a disconnection. The equivalent reactions are mainly ionic that involve nucleophilic displacement by SN1 reaction, SN2 reaction or carbonyl substitution with amines. So generally these one group CX disconnection would involve a nucleophilic displacement. Now when I say nucleophilic displacement, easily we can understand that either it can be SN1 reaction or SN2 reaction, or if there is an attack of lone pair of electrons on carbonyl system with the help of amines. Now this can be one of the example where we can understand about CX disconnection. Now for example, if there is a presence of a carbonyl group like this, if an NH2 lone pair of electron goes and attacks, we will be able to form a C single bond N. That means we will be able to form a C single bond N bond where a disconnection can take place. This is also true when there is a presence of alcohol system, thiol system or on carbon electrophile system. Now in this case, the carbon is going to act as an electrophilic system. We can observe that in C single bond O, C single bond N or C single bond S, oxygen, nitrogen and sulfur, they are going to carry negative charge. So obviously carbon is going to carry a positive charge, which is going to lead that system to an electrophilic system. The normal polarity of disconnection, now when I observe an RX, will be a cationic carbon. That means carbon will carry a positive charge, that is cationic carbon synthon, and an anionic heteroatom. That means the heteroatom like oxygen, nitrogen and sulfur will carry a negative charge. This is characterized by acyl or alkyl halides. Whenever we observe an acyl halide, that is C6H5 CH2Cl, or alkyl halides like C2H5Cl, as electrophiles, and amines, alcohols or thiols as nucleophiles. Now when we observe such situations, Where there is a presence of carbon and an heteroatom, oxygen, nitrogen and sulfur would always carry a negative charge and carbon would carry a positive charge. Unless and until there is an Ampoulang situation, this is how the natural synthetic cleavage will take place. Now for example, we have got this Rx. There is a cleavage between C single bond X. That means I am trying to do a one group disconnection. Here I am going to get a synthon as R is going to carry a positive charge and X is going to carry a negative charge, giving me synthetic equivalents as R, HAI and HX. Now this can be HBr, HCl, so on and so forth. And here RHAI can be RCH2Cl or it can be any kind of carbonyl carbon system. Alternatively, there is also a possibility to use the reverse polarity with nucleophilic carbon synthon and an electrophilic heteroatom synthon. We have observed this as an Ampoulang polarity where we can give a negative charge to carbon and a positive charge onto the heteroatom. But these types of disconnections are only possible when there are second or third row elements such as sulfur, silicon, phosphorus and selenium. So in this one group disconnection system, if I want to do an Ampoulang system, that means I want to do a reversal of polarity, second or third row element should be involved in the molecule. Now those elements are sulfur, they can be silicon, they can be phosphorus and selenium. In these case, these sulfur, silicon, phosphorus and selenium, they will carry a positive charge and carbon will be carrying a negative charge respectively, giving me an Ampoulang type of system. Now these synthons are characterized by organometallic compounds. We can observe that these systems can be observed through an organometallic system which can be RLi, RMgBr. Now this can be C2H5Li. That means lithium is going to carry a positive charge, carbon is going to carry a negative charge. In your Grignard reagent, MgBr is going to carry a positive charge and carbon is going to carry a negative charge. And compound such as RSCl, trimethylsilyl chloride, diphenyl phosphorus chloride, all such molecules here in which the carbon is going to carry a negative charge and the heteroatom is going to carry a positive charge. Now in this way we can observe a one group CX disconnection through a normal synthetic analysis where there is a natural synthon like carbon carrying a positive charge, or they can be an Ampoulang system where carbon is going to carry a negative charge. In this way, if I want to do the same one group disconnection, how will I carry out? Rx, again there is a cleavage between R and X. Here carbon system is carrying a negative charge and the X system is going to carry a positive charge. How do we get this particular system is, we have to observe that we will be getting this in terms of RLi, RMgBr or XCl. Now this type of synthetic equivalents have to be observed if I have to turn this self into an Ampoulang system. Now common example of doing a one group disconnection system would be carbonyl derivatives. Now carbonyl is represented as RCOX, which corresponds to carboxylic acids and their derivatives. Now carboxylic acid is nothing but RCO2H. Their derivatives can be RCOCl. Their derivatives can be an ester, RCOOCH3, so on and so forth. We can observe here that either it can be an ether derivative, an acyl chloride derivative or a carboxylic system. In these molecules, the point of disconnection is the bond between the heteroatom and the carbonyl group. So where do we disconnect in this particular system is, if there is a presence of a carbonyl group and an heteroatom like this, we will be disconnecting at this particular position and hence we will be doing a one group disconnection. Therefore, we can make ester and amides from acid chlorides and alcohols or amines respectively. So how do we synthesize an ester? Ester can be synthesized by reacting a carboxylic group with an alcohol, giving me RCOCl, RC double bond OOCl. or OCH3, or amide can be synthesized as RCONH2. Acyl chloride can be RCOCl. Now for example, if I start with an ester, we can observe here that I can cleave at this particular position. There is an heteroatom and a carbonyl carbon. I am cleaving between C single bond O to give me one synthetic equivalent as an alcohol and the other synthetic equivalent as an alkyl chloride or acyl chloride. In the same way, if there is a presence of an amide system, what is amide system? RCONH R-. Here again I am going to cleave this particular system between carbonyl carbon and nitrogen. The cleavage is between C single bond N. Here the starting material can be one of the system is amine and the other system is an acyl chloride or an alkyl chloride. So if I want to synthesize my target molecules, how I would do? Alcohol reacts with alkyl chloride or acyl chloride to give me respective ester. Acyl chloride or alkyl chloride, it is going to react with an amine to give me an amide system. So such simple systems can be dealt under one group disconnection. The ester is simply made this way. This ester has been used both as an insect repellent and the solvent for perfumery. One of the example in which esters are important are, they can be used as solvent system, they can be used for perfumery systems because esters have very pleasant smell. Now if in the same way I want to do one particular example with ester, the common ester is called as benzoyl ester. Now this particular structure which is the target molecule, it is called as benzoyl ester. Now if I want to cleave, now this analysis, it discloses two accessible compounds. One will be benzyl alcohol, the other one will be benzoyl chloride. Now I can observe here that I can do a cleavage between C single bond O, giving me a benzyl alcohol and a benzoyl chloride. When we do a reaction, that means merging these two in the presence of pyridine as a solvent and a catalyst, it is going to give me the ester. So benzoyl chloride reacts with benzyl alcohol to give me this particular benzoyl ester. This is a very classic example for ester which can be used as a solvent and also in perfumery. Here you can observe that I have just done a one group disconnection, that is one group CX or 1CX disconnections. Apart from the ester systems, we can observe that acid chlorides are regularly observed. Now when I say acid chlorides are regularly observed is, either it can be in the synthesis of an ester, either it can be in the synthesis of an amide. We can observe that acid chlorides are one part which are regularly used in such type of synthesis. This is because they are most electrophilic of the acid derivatives. That means easily they can be attacked and easily the chlorine system can leave. That means once they get attacked, that means lone pair of electrons on oxygen, if it is going to attack onto the carbon and carbon, easily the chloride is going to leave, and hence they are the best systems for the synthesis of esters and amides. And they can be synthesized from acids themselves with PCl5 or thionyl chloride. So acid derivatives or acid chlorides, they can be synthesized by when acids react with PCl5 or thionyl chloride. Now this can be seen as an example when RCOOH, that means RCOOH, that is acid, it is going to react with PCl5 or thionyl chloride, it is going to give me an acid chloride. So this is how acid chlorides can be synthesized. The other significant acid derivatives can be made from acid chlorides or from any compound above them in the chart of reactivity. Now we can observe that most of the time acid chlorides have been utilized because they are most reactive species and most electrophilic species, and easily many of the compounds could be synthesized with this particular system. Hence, while doing a one group disconnection, generally one of the synthetic equivalent that we achieve would be a system containing an acid chloride system. Now when we observe this, if I observe this system which is going to say about the most reactive system and the least reactive system, under which acid chlorides are most reactive and amide systems being least reactive system. How are acid chlorides synthesized? When an acid reacts with thionyl chloride or PCl5, I am going to get an acid chloride. When an acid reacts with an acetic anhydride system, I am going to get an anhydride. But their reactivity is less than that of acid chlorides. How do we get an ester? When an acid reacts with alcohol in the presence of a protonic environment, I am going to get an ester, but their reactivity is lesser than that of anhydride system. When an acid reacts with an amine system, that is RNH2 system, I am going to get an amide system, which are the least reactive system in this particular system. In all these systems that we have synthesized, we can easily do a one group disconnection, and one of the synthetic equivalent that we can achieve, it is acid chloride system. Now for example, if I want to see acid chloride, here also I can do a one group disconnection. Anhydride, another one group disconnection. If I want to see ester, one group disconnection. Amide, one group disconnection can be achieved. So whenever it is possible that there is a presence of a carbonyl carbon and a heteroatom, I can easily achieve a one group disconnection, and in turn I can observe that easily I can do a one group disconnection and I can achieve my target molecule by doing its respective synthesis. Most of the time one of the synthetic equivalent will be an acid chloride respectively. Now for example, propanol, which is a weedicide in rice fields. Now this particular compound that is going to be dealt as an example, it is called as propanol. The structure is this. Now in this particular propanol system, we can observe there is an amide system. So amide disconnection yields the amine which can be made from orthodichlorobenzene by nitration and reduction. So how do we do this disconnection? So the target molecule is called as propanol system. We can observe that there is an amide system. Amide meaning what? There is a carbonyl carbon and an heteroatom. So what I can do? I can do a one group CX, that is one group disconnection. If I do a one group disconnection between C single bond N, I will be cleaving an amide. In turn, I will be ending up with NH2 system. So 1,2-dichloroaniline system. When I say dichloroaniline system, NH2 cannot be synthesized directly. So what we have to do? We have to do a functional group interconversion. So NH2 is getting converted to NO2. And easily when I cleave this C single bond N, I will be able to get a dichlorobenzene as my starting material. And then after nitration I can get my nitro group introduction. And in the presence of ethyl chloroformate, we can get our target molecule. So this is how we do its retrosynthetic analysis. Now whatever we have done is the retrosynthetic analysis. Now we would be trying to synthesize this particular compound. So the starting material is 1,2-dichlorobenzene. It reacts with HNO3 and H2SO4 to give me nitro-dichlorobenzene. Nitro group in the presence of hydrogen and palladium catalyst gets converted to NH2. This particular system, that is an substituted aniline system, it is going to react with ethyl chloroformate. What happens here is lone pair of electrons on nitrogen is going to attack onto the carbonyl carbon of ethyl chloroformate, so that I will be able to get my target molecule, that is propanol system. The same way, if I take up other type of example in terms of ester, what I can do is, if there is a presence of an ester, I can cleave between C single bond O here, and then I can get an acid and an alkyl halide. But most of the time such types of approaches are avoided, because sometimes it is difficult for us to get its respective synthetic equivalent. But the other disconnection approach for the ester into an alkyl group and heteroatom is also possible by the use of an anion of the acid and an alkyl halide. But since what is going to happen is, this particular anion may be stable, may not be stable, and hence we might able to avoid such type of systems. The next type of example which can be seen under one group disconnection would be the synthesis of ethers. The disconnection approach for the synthesis of ethers also targets the bond C single bond O. There is a possibility of a bond cleavage from either side of oxygen, as there are two C single bond O bonds present in the ethers. So whenever we observe an ether system, I can observe that there is a presence of, we can observe here that there is a presence of an ethereal system which is going to have a 2C single bond O systems. Now, to consider this, which is a proper route, generally we design two routes when there is a presence of ethers. It can be either route A system or route B system. Whichever is the convenient system and which is going to give me a proper synthetic equivalent without any type of sub-reaction system, that particular route can be chosen for the synthesis of ester. Now for example, if this is my target molecule, there is a presence of an ether. There are two routes that are considered. One is route A, the other one is route B. In route A system, when there is a cleavage, we are getting benzyl chloride and an alcohol as the starting material. And in route B, I am going to get a benzyl alcohol and an alkyl halide. Now the reaction can take place by allowing the reaction of an alcohol with a base in the presence of sodium hydride. The alcohol gets converted to an alkoxide ion which further reacts with benzyl chloride is more react with the benzyl chloride to the ether in 85% yield. This is with respect to route A. Why do we prefer route A? Now in route A what we are doing is alcohol in the presence of base like sodium hydride. Now this proton is abstracted. Once the proton is abstracted, negative charge on oxygen will go and attack onto the carbon system and the chlorine is going to leave the system, giving me my target molecule. We prefer route A because benzyl chloride is more reactive and it does not undergo any elimination reaction. We can observe here that there is no chance of undergoing any elimination reaction. But when I observe route B, there is a presence of an alkyl halide. This alkyl halide can undergo an elimination reaction and hence route B is not the preferred route for the synthesis of this particular ethereal system. Hence in route B, what is happening is because the alkyl halide can undergo an elimination system and hence only 50% yield can be achieved, hence that particular route is not preferred. So what is the proper route that we do? There is an alcohol that is present in the presence of sodium hydride. It gets converted to an alkoxide. This alkoxide is going to react with the presence of a benzyl chloride to give us the target molecule and hence route A is preferred. The next example in this particular system is allyl phenyl ether. Again there will be two disconnection that can happen. The allyl phenyl ether can now have either path A as the disconnection or it can have a path B as the disconnection. Path A is disconnected to give me a bromobenzene system and an allylic alcohol, and path B is going to give me a phenol and allylic bromide system. So this is my target molecule. Now here the target molecule is said to be allyl phenyl ether. Again there are two routes. One is route A and route B. Under route A, I am going to cleave so that I am going to get an allyl alcohol and a bromobenzene. Under route B, I am going to get a phenol system and an allylic bromide system. Now when I observe, route B is more favorable because nucleophilic substitution on bromobenzene are very difficult. Hence the possible synthetic pathway is given as, when I take phenol in the presence of NaOH. Now phenol in the presence of NaOH, the proton is lost. I will be getting an alkoxide. This is going to react with an allyl bromide system. Now this is the allyl bromide system and then I will be getting my target molecule. In this way allyl phenyl ether can be synthesized, and hence route B is preferred over route A. This is because substitution on the bromobenzene becomes very difficult because OH is not a good leaving group. It is very difficult to abstract the proton from the alcoholic system. Whereas when I do the same system under phenolic system, phenol in the presence of NaOH easily gives away its proton and it is going to give me an alkoxide ion. This is going to attack onto the carbon, and bromine is a very good leaving group, and in turn it is going to give me my target molecule. Another type of example under one group disconnection would be the synthesis of sulfides. Sulfides are organic compounds having chemical structure RSR, where R and R, these two R can be symmetrical, that means they both may be the same, or they may be unsymmetrical when this R and R dash are not same. The disconnection approaches for sulfides are similar to that of ethers. Now this is because either it can be cleaved at this position or it can be cleaved at this particular position, and hence under similar grounds that we have done for an ethereal system, even sulfide systems can be cleaved. Now the disconnections are in such a way that we can either disconnect at this position and this position. C single bond S, which is a sulfide system. One of the system can be an alkyl halide, the other system is sulfur carrying a negative charge. This can lead me to a thiol system. The reaction is simpler with sulfur in comparison with two ethers, because sulfur is a good reactive system than that of oxygen. Sulfide anion are more nucleophilic. If I compare the nucleophilicity of oxygen and sulfur, sulfur is having more nucleophilicity than that of oxygen, and they are more nucleophilic towards saturated carbon than the alkoxide. O minus, they are less nucleophilic towards the carbon, and hence sulfoxides are more nucleophilic towards the carbon. And also in the sulfide system the risk of elimination is very less. So if I do such kind of disconnection, I will be easily disconnecting C single bond S to get me an alkyl halide and a thiol system. Now under this particular category, a common example is called as chlorobenzyl. Now this is one of the acaricide. This can be learnt under pesticides and insecticides also, in which there is a presence of a sulfide system. The disconnection of this particular molecule yields an acidic thiophenol and a reactive alkyl halide. The synthesis, it is going to involve combining these two in ethanol with sodium ethoxide as a base. So how do I do a cleavage? I will be doing a cleavage at this particular position where I will be cleaving C single bond S. I will be getting one system which is a acidic thiophenol system. The meaning of acidic thiophenol is proton can be cleaved out easily. The other one is called as alkyl halide system. Symmetrical sulfides can be synthesized from alkyl halides and sodium sulfide. Now before I go to this particular system, when this alkyl halide reacts with this thiophenol system, it is going to give me the target molecule, that is my chlorobenzyl system. This is when the system is unsymmetrical. Now when the systems are symmetrical, we can make use of alkyl halide system and sodium sulfide. The product forms in the first step is a monoanion required to prepare the C single bond S bond. The synthesis is merely the combination of alkyl bromide with sodium sulfide and ethanol. If there are symmetrical alkyl halides or symmetrical sulfide system, what we are going to do is we are going to cleave the system in such a way that both the systems are cleaved off, and hence one group CX disconnection 2 times we are doing, so that one of the group is an alkyl bromide, the other group is also an alkyl bromide, and the other is a dianion system. How do I achieve this dianion system? When I convert that into sodium sulfide. So sodium sulfide reacts with 2 mole of alkyl bromide to give me symmetrical sulfide system. Unsymmetrical sulfide system and symmetrical sulfide system could be done under a one group CX system through a retrosynthetic analysis. The next category under the same one group disconnection would be compounds that are made from alcohols. Several nucleophiles can be used in these reactions. We can observe that alcohols are a very good reacting reagent system where several nucleophiles can be used. In every case, a nucleophile heteroatom displaces a leaving group from a compound derived from the alcohol. That means one of the system will act as a leaving group and which is going to be derived from the alcohol. Alcohol is a good starting material for compounds like ethers, sulfides, thiols, alkyl halides. We can observe that most of the compounds could be synthesized by the alcohol as the starting material. Now for example, if there is a presence of an alcohol, if it reacts with an alkyl halide in the presence of another alcohol, in the presence of a base, it is going to give me an ether system. Alcohol gets converted to RCl. If this alkyl chloride reacts with another molecule of an alcohol, it is going to give me an ethereal system. Alcohol can be converted to alkyl bromide, which in the presence of a thiol system, it is going to give me a sulfide system. Alcohol reacts with tosyl chloride, which is going to give me a tosylate system. This tosylate system, when it reacts with a thiourea, it is going to give me thiol system. This is possible when tosyl chloride, alcohol reacts with tosyl chloride in the presence of NaOH and water. This tosyl chloride, again in the presence of NaOH and water, in the presence of thiourea, these systems, they give me a thiol system. Next, alcohol in the presence of mesytyl chloride gets converted to ROMS, that is mesylate. This, under the presence of various nucleophiles, they are going to give me various other types of derivatives like RBr, RCl, Ri, so on and so forth. When alcohol in the presence of pyridine and an acyl chloride or an RCOCl, this is going to give me an ketonic system. In this way, we can observe that alcoholic system is a very good starting material for the synthesis of ether, sulfides, thiol systems, or they can be a ketonic system, mesytyl system, tosyl chloride system, so on and so forth. So if I want to do a retrosynthetic analysis, I would simply want to cleave an ROH and then in such a way that RO and either the proton cannot be replaced over here. So what we have to do, we have to just cleave between ROH and it has to be turned in such a way that it is going to now have a good leaving group. In turn, further when it is going to react with the next reagent, it is going to give me a proper new type of derivative. Now such type of derivatives can again be dealt under one group disconnection. Ethers can be dealt under one group disconnection, sulfides can be dealt under one group disconnection, thiol system can be dealt under one group disconnection, and also these mesytyl systems can be dealt under one group disconnection. We have already discussed in how in a systems like ethers and sulfides could be dealt under one group disconnection. So this gives an overview of one group disconnection and how they can be applied for carbonyl compounds, ethereal systems and sulfide systems respectively. Thank you.